Okay, so let's get started. Uh, Yesterday we left off on Laplace transform. Just a quick review from yesterday about Laplace transform. Basically, what it does is it's an operator that turns something from the time domain into the frequency domain. We express the time domain in t, and then we translate it into the frequency domain, which is in the complex, which is a complex number where s is equal to sigma plus j omega. So the real component is sigma, and then our imaginary component is represented as omega. And the reason why we do this is because when we uh, put this into the exponential, the frequency component omega will pop up as sine and cosine, while our real component will pop up as a decay, which will relate to stability properties later on. Um, are there any questions on Laplace transform? And we'll start with an example as well, so you can see the application of how we can turn a differential equation, or how we can solve it without the traditional method. Okay, so let's go to our first example. Well, it's only our only example in this section. And we're just going to go back to that mass spring damper from the earlier page where we just have this mass and we have applied force F of t. And actually, we're not going to have a damper in this example. We're going to cut that out. We're just going to have a spring instead. So this is going to be a little easier. Okay, we're going to define going right as positive. And in this case, when I draw this arrow with x of t, that means I want to track the position of this mass. So if I apply a force F of t to this mass, I want to predict where its position is going to be. Okay, so when we look at the free body diagram, we're going to have our input force F of t being applied. And then to counteract that force, we have our spring um, kx. All right. So then if we do sum of the forces is equal to mass times acceleration, which is x double dot, we get F of t because it's going right, it's positive, minus kx because it's going to the left, which is negative. So this is our differential equation. We're going to move everything to the left-hand side for x. So we get mx double dot plus kx is equal to f of t. And that should be it. So that's our differential equation. So I'm going to so we want what we want to do is we want to take the Laplace transform of this differential equation right here. So I'm going to mark this as 1. So we want to take the Laplace transform. So I'll just denote it by this curly L with this empty bracket. So this is our operator of equation 1. And before I do that, what I'm going to do is I'm going to copy the table from the previous page so you can see what I'm doing. Oops. Let's go up here. I'm going to copy this property. Actually, I guess we don't need that many. Just copy that. Yeah. Will it paste? There you go. Well, we're at the very beginning of the slide. All right, there you go. So now we have this property here, so you can see what I'm doing. Okay. All right, so if we take the Laplace transform of this whole differential equation, so we get mx double dot plus kx is equal to f of t. Well, if you look here, I'm gonna highlight it. This is the linearity theorem. Mass times x double dot and spring constant times x, they're both constants. We can just pull out. And if we look at f of t, if we take a Laplace transform of just f of t, it just becomes f of s. So I'm going to do the right-hand side first. So we're going to do f of s is equal to the Laplace transform of mx double dot plus the Laplace transform of kx. And note that I can split them up because it's linear. And then if we look at the Laplace transform of a derivative, which I'm going to highlight now, it's going to be s squared times x. Well, let's multiply. Forgot the m. It's going to be s squared times x of s minus s times s times the position of x at 0 minus the first derivative of x at time equal to 0. Okay, plus k times x of s. One thing to note is that when they say time is equal to 0 minus, it means that if I were to look on, if this is time t equal to 0, and let's say this point here is infinitesimally small, where this is a very small t, 0 minus is going to be right here. And this is like negligible. They're basically the same spot. But basically, this is a guarantee that this is like right before anything turns on. But you can treat it as these two are basically the same for this class. Any questions on what I did so far? Yeah, well, usually in homework or on exams, I'll tell you if there are initial conditions. I forgot to specify, but let's assume 0 initial conditions, meaning that this mass is not moving at time equal to 0, and its position is also at neutral or at 0 at time equal to 0. So then we can make those terms go away. So now we're left with f of s is equal to m s squared x of s plus k x of s. Then we can separate our terms. And we get f of s is equal to x of s multiplied by ms squared plus k. And then when we formulate it into our transfer function form, like finding the transfer function, transfer function is defined as the output over the input. So then our output is, we defined it as position, and our input is force. So then we want x of s to be on top and force to be on the bottom. And then we get 1 over ms squared plus k. So that's our answer. Now, if maybe, let's say, if I see, if initial conditions are not 0, we actually leave the terms in there. And I'll just give you the final answer and you can work it out. We get this term here. So we can't explicitly separate the force and the position when we have non-zero initial conditions. So instead, we have to represent it as an output. Our output x of s is equal to 1 over ms squared plus k multiplied by a force plus s times our initial condition plus the velocity at the initial condition divided by ms squared plus k. So then here, and we'll talk about this more later, this is our forced response because it's our response based off of our input. And then this is our natural response, which is based off of our initial conditions. And this is our output. And this is the output in the this is the output for the position in the frequency domain. Position in the frequency domain. Are there any questions? So when you look at this, what this means is the transfer function is always going to be your system with a force response, and it's assuming that we're looking at the force response only. So if I ever ask you to find the transfer function and but the initial conditions are not 0, your transfer function is going to be, you still choose, this is still going to be your answer because you're going to be ignoring the initial conditions. But if I ask you to find the response of the system with initial conditions, you have to use the equation on the right-hand column. One last thing, and I'll bring this up later. So this is the output in the, this is the output for the position, but if I want the velocity as the output, what would I need to do to modify this equation here on the right-hand side? If we look at our table, what would I need to, what's the equivalent version of the velocity in the frequency domain? It would be, if we're looking at this column, the derivative of my function. Yeah, so property 7, I think that's 1, 2, 3, 4, 5, 6. Yep, property 7. So if I want velocity, if I want, I guess, v of s, which is the velocity, I'm going to define that as s times x of s. So when you multiply this by s, that's the equivalent of taking the derivative in the frequency domain. So this is the velocity. So then I would just multiply this whole equation above by s, and that's going to be the velocity in the frequency domain. So then I guess a of s, which is the acceleration, is going to be equal to the double derivative of the position. So this is going to be property 7. Seven and 8. So then likewise, if I want to take the integral, I would divide it by s. Okay. So the Laplace transform can be used to arrange the system to be a ratio of the output to the input. So this is the formal definition. The transfer function is the ratio of the output to the input in the frequency domain, or also known as the complex domain, because it's in the complex domain where s is a real number plus a omega times j. So then here we have our system G is equal to our output, which is C, divided by our input R. And then we can rearrange it as output is equal to our system multiplied by our input. So think of it as our output is equal to our system multiplied by the input response. So then once we rearrange our Laplace, or once we rearrange our transfer function into this form, when we take the inverse transfer function of this form here, we can then get our time domain solution. One thing I want to note here is that sometimes if I write g of s for a transfer function, it's very contextual. G of s is just a generic system. There have been confusion in the past where we frequently use g as the open loop transfer function. And I just want to go over real quick that right now. So we have a negative feedback system here. And if I want to look at the transfer function of this system, if we have C here and R here, our actual transfer function for the system, we're going to be using feedback form, is going to be equal to G divided by 1 plus GH. So here G is just our system, but we're using, this would be equal to G here. I guess that's confusing. So this would be that. So then I guess a better way of writing it is this. So there has been confusion in the past about this. So it's just context. At the end of the day, you should always be looking at output over input and seeing what the equivalent system is with output over input. So you can do block diagram reduction to figure that out. One other side note about this is that when I talk about open loop transfer function, I'll put it on the left-hand side. It's going to be equal to G times H. And this includes a sensor. while my closed loop transfer function is going to be g over 1 plus. So the reason why this is the open loop sensor includes a sensor is because what we're doing is we're taking this signal, it goes through G, and then we measure it through the sensor, but we don't include the feedback. It's an open loop. And we're measuring that system's output with a sensor. So we have to include that as part of the transfer function. So whenever I talk about open loop transfer function, it's going to be this G multiplied by whatever is in the feedback diagram. This is the open loop. While I'll do a different color, the closed loop transfer function is going to follow this line. It's going to go through our feedback. Then it's going to go back into our sensor again. And that's the closed loop transfer function. And then it comes out like that. And there can be cases where your open loop transfer function is unstable, but when you close the loop, it becomes stable. Yeah.
Equation for transfer function with initial conditions.
Okay.
We get it to the transfer function form with x or if we have initial condition.
Oh, yeah. So the question is, can we get this transfer function form when we have initial conditions? So basically the inherent, or I guess the transfer function equation implies that we're only looking at the force response. So when I ask you to find the transfer function and I give you initial conditions, you're going to derive this, but then we're going to basically just ignore the natural response because that's not the definition of the transfer function. The transfer function is defined as the output over the input, so it's only looking at the force response. So in this case, you would be looking at this component here. This is the transfer function because it has this input here. And then, but it's the same as this one where I said, oh, assume the initial conditions are 0. They're the same. It doesn't change with initial conditions. You're just basically looking at the forced aspect only.
So basically, in this equation, the left side shows the system, and the right side is only considering the.
Yeah, well, the right side is actually the full picture. The right side includes the total response, while the left side is only the forced response. Yeah. Yeah, so if I were to have a generalized equation where I don't know if initial conditions exist or not, the right side's the full solution. So the right side is actually more correct in that sense because it applies to both 0 and non-zero initial conditions because we can always just make them 0. Then when we make them 0, it becomes the transfer function because the transfer function only looks at the input response, which is the first term. So right here, this is just the forced response. But yeah, it can get, I guess it's like it just gets a little bit like it gets a little bit confusing when you include initial conditions, but basically the transfer function only cares about the input response and not initial conditions.
So what if we don't have any forcing function, but we just give some initial conditions to the system and let it play?
So then f of s would be 0. Then we just get the right hand. We only get this term. So the question was, if we don't have a input, then what we would get, we would just get the natural response only. F of s is equal to 0. And then we just get x of s is equal to the natural response only. Good. These are good questions because this can get very confusing very quickly if we rush through it. This is a very important chapter. So if you are confused, it's good to slow me down. Also, less material to be covered on the midterm if you ask me questions. Okay, so So that's the definition. What I wanted to do now is I wanted to continue that example because now what we're going to do is we're going to find the time domain solution. So basically, we want to find the output x of t. And you know what? And let's also find x, the derivative of x of t from the previous example. And I'll upload these notes today because we'll finish the set of notes for a unit impulse. And when I say unit impulse, it means it's just equal to 1. And we're going to assume this time zero initial conditions. We're going to assume zero initial conditions. And I'll just write out the equation. Our transfer function for our output is equal to 1 over ms squared plus k multiplied by f of s. I'll just tell you from memory from the table, a unit impulse f1 is f of t is equal to the Dirac t, where we just have this turn on at time 0 up to a unit of 1 and then go back down to 0. Or I guess the better definition is we have this peak go up. I believe this area is going to be 1 equal to 1. Well, when we take the Laplace transform of it, it's just equal to 1. So that means f of s is equal to 1 here for a unit impulse. Okay, so then we get our output is equal to 1 over ms squared plus k. And one thing I do is I always get rid of this term on the first term here. I would like it by itself. I want s squared by itself, so I'm going to divide everything by 1 over m. So we get s squared plus k over m. And so I'll let you copy that down. Okay, I'm going to take a screenshot of this table again because I need this property now. Actually, we only need the last 2 lines. Why did it go all the way to the top again? Apologies for that. Okay. I'm going to try this again. Oh, there you go. That's better. All right, perfect. So if we look at this table here, on the left-hand side, this is f of t. On the right-hand side, it's f of s. So that's the frequency domain. So if we were to take the Laplace transform of sine, we would get that. If we were to take the Laplace transform of cosine, we would get that. When we have a mass with a spring with no dampening, I know the response is going to be oscillating. So educated guess makes me think that we're going to have something that looks like this. So when we look at this here, What does this most closely resemble to? Number 6 or 7? 6. Yep. So it resembles 6. So we need to get this. We need to make x of s resemble property number 6. So the reason why I wanted to divide both sides by m is because I wanted this s squared by itself. And here, we can't change the denominator terms, but we can pull constants out of the numerator. So here, basically, property 6 tells us that omega squared, so s squared plus omega squared is equal to s squared plus k over m, which means that omega is equal to the square root of k over m. So then we want x of s is equal to some constant. I'm going to call this E, I guess. No, I'm going to just do k with these little terms here. When we pull that k out, is equal to omega over s squared plus omega squared, which is equal to k multiplied by square root of k over m divided by s squared plus k over m. And basically we want this equal to the above equation now. 1 over m times s squared plus k over m. Turns out that this k here, capital K here, is equal to 1 over square root of k over m. So then we get x of s is equal to 1 over square root of km multiplied by square root of k over m times s squared plus omega squared. Any questions on the last 2 or 3 steps? Is there a chat question? Okay, nope, good. All right, so now that, so this is good because now we have this is still equal to that. So these two are the same. And we can now take this property and we can go back to, oh, where did the omega go? Oh, sorry. Actually, this should be k over m here. You were asking where did omega go in what relation? So right here, we just found that omega squared is equal to k over m, and then we found that omega is equal to that. We know that, maybe I'll do a different color. This equation is equal to this equation multiplied by a constant because we can manipulate the numerator term, and then we just solve for that term. So I'm not sure exactly what you mean by where did omega go.
So if x of s is equal to the f of s for property 6 is omega over s squared plus omega squared.
Where did the if you want to clarify that, but I'll continue while in the meantime. So then now that we have that, we can just work backwards. So when we take the inverse Laplace now, so take the inverse Laplace transform of x of s, and that'll get you x of t. So the inverse Laplace transform of x of s is equal to 1 over square root of k times m multiplied by it's going to be sine omega t. In this case, omega is going to be root k over m. T times u of t. And you can just leave the u of t out if you want. The u of t just tells us that this is 0 before time is equal to 0, but you don't have to leave it in there. So that's it. So that's our this is our solution in the time domain, and that's how we solve it using Laplace transform. We don't have to guess what the solution is using methods taught probably in your differential equations class. Now, if we were to find x dot of t, we can just take the derivative, and that's just going to be 1 over m cosine of root k over mt. But if we were to do it using the other method where I say we were to take the inverse Laplace transform of s multiplied by x of s, that's going to get us x dot of t. So let's do that. So s x of s is going to be equal to going to be equal to 1 over m multiplied by s divided by s squared plus k over m. So you notice here, we don't want any constants being multiplied in the numerator. So we can pull the 1 over m out. This is equal to s over s squared plus k over m. And then when we take the inverse Laplace transform of it, we get x dot is equal to 1 over m cosine square root of k over mt. So we both get the same solution. Cool trick, right? Okay, maybe I find it cool. I don't expect you to find it cool. Anyway, so that wraps up this chapter. So we're done with chapter 2. Oh, Son likes it. All right, cool. I'm not sure if that's sarcasm, but I appreciate it. It will get more complicated because it's not always this simple. If I have dampening, it's going to be a little bit more complicated, and I'll go over an example on that in chapter 4. Just some takeaways from this chapter. Because we talked about math, the eigenvalues of A is used to determine stability. I'll talk about what A means and how to find A in chapter 3, which is going to be what we're covering next. Just know that positive eigenvalues are unstable and negative eigenvalues, like only negative eigenvalues are going to be a stable system. The minute you have one positive eigenvalue, it's unstable. ODEs are used to model the system and show how the inputs affect the outputs. We also, if we include the initial conditions, we can actually figure that out too using Laplace transform. And in this example, Laplace transform is used to easily solve differential equations. Maybe I shouldn't put easily, but it's easier than the other way of guessing. Transfer functions allow us to explicitly separate the input-output in the system. Know that the transfer functions only look at the input, the force response. We don't consider the initial conditions. If I ever ask you for the total response, include the initial conditions. If I tell you to give me the transfer function, you can just give me the natural response or the force response form only. So that wraps up this. I'll upload this slide. Today, we're going to start chapter 3 and hopefully finish it. Well, this is chapter 3 and then a section of chapter 4, which I think is very related to chapter 3. I don't know why they separated it. So before we get started, I just want to tell you the purpose of it before we just jump into the trenches. So chapter 3 is a linear state space representation, and it's used to reduce higher order systems to a first order differential equation or representation in matrix form. So the reason why it's so beautiful is because we know the solution to a first order differential equation. It's pretty easy. So we can take any higher order differential equation and put it into a first order differential equation in matrix form. And that's a very beautiful property. This is very useful for MATLAB and computing software that excels in matrix operations. So MATLAB is very favorable when you do matrix multiplication. It loves that. And it's easier to have stuff in state space representation. You're more likely to avoid computational errors. Guaranteed that you'll use this in all of your controls classes. And in controlled papers, like if you read about these research papers, you will read about problems that are formulated with state space representation. Not always, but it's not uncommon to see it in state space representation. So this is also a particularly useful chapter for research. So basically what I'm saying is that this is an important chapter as well. So we're going to go over basically all of chapter 3, and then we're going to talk about solution to state spaces, which is the end of chapter 4. I think these two are very tied together, so that's why I put them together. So from lecture 2, we talked about what conditions will make time go to infinity. Well, that's when we have an unstable system or a positive eigenvalue. And then on top of that, when we're solving for these differential equations, it's hard to solve in the time domain. And one way of doing it is using the Laplace transform. So this is using Laplace transform. And then the second form is actually solving it in state space form. So this is just another tool for you to solve and guess what the output response is using state space representation now. It's got some cool proofs coming up. Maybe I think it's just me again, but it's okay. So we're gonna talk about state space first. So when we're talking about state space, dynamic systems can be modeled using physics via differential equations. And then basically what differential equation tells us is it's used to describe how the input and output of a system behaves. So this is nothing new. I mean, we go back to that mass spring damper again, because I find it fairly intuitive. If we have our spring kx and our dampener, and we have our differential equation. It's going to be mx double dot plus plus bx dot plus kx is equal to f of t. Basically, what state space will tell us is how all of these states are related. And what do I mean by that? So basically what we want to see is how the system is changing. So think of it as the derivative is equal to our current states. And this f here is not force. It's a function. This is a function, not force. And basically, how the system is changing is going to be a function of our current states. And if we look at this, we can draw this relation where acceleration, it changes our velocity. Velocity changes position. And because of our spring, when we compress or expand it, that compression is going to change the force acting on the spring, which is going to change the acceleration. So our position actually changes acceleration. So then we get this relation where these states are related to each other, where our position and velocity will change the acceleration. And this relation allows us to observe different outputs as well. We can take the derivative of position to get velocity. We can take the derivative of velocity to get acceleration. So they're very interrelated. So this relation allows us to observe different outputs. Any questions?
Yeah, I'm trying to see how position actually changes the acceleration. So can we figure it out from the differential equation?
Right here, how position changes acceleration. Well, yeah, if we were to rewrite acceleration, and actually it's not just position, the velocity will affect it too. Um, we can rewrite our differential equation as this. And actually, to be more thorough, I should put x of t, and so you can see here now that both velocity and position will affect the acceleration in our differential equation. So in a way, they're both related, you know, if I were to draw it like that. That's probably a more accurate way of describing this relation. Maybe I can do it like that, or that's an integral. But the point is they're all related. So if we look at, so this is a general representation of state space, very general form. And sometimes this is the nonlinear representation, general form of state space. So for any arbitrary dynamic system, we can look at the state and change in energy. So basically what we're looking at is we're looking at how energy is being transferred within a system, if we're thinking in terms of mechanical systems. And this is going to, so this x here is actually our state vector. It's a vector containing all of the state variables, but in this form, it's the derivative of the state variables. So this is the derivative of state variables. And we'll actually continue on tomorrow. It's 11:20. All right. One last thing. I have changed my office hours because of some scheduling issues on my end. So office hours is going to be a different time. I'm trying to also be accommodating for people who work. So on Thursdays, office hours is going to be right after class from 11 to 12:30 and MEB 236. And then online, it's going to be online from 4:30 to 5. On Tuesdays, I also have online office hours from 4 to 4:30. So just use the lecture Zoom link. All right, thank you. And do you have a question, Elena? I can answer real quick before I go.